So here we have Benjamin Chung, who is a modeling and simulation consultant in Julia Hub. And previously he was a postdoc at the University of Washington. And his talk is going to be about synchronous systems in ModelingToolkit. So let's welcome our speaker.
Awesome, thank you very much, and I apologize for the delay on this. I'll try to be quick to stay on time. So yes, I'll be talking about synchronous systems in ModelingToolkit and generally about discrete time modeling in ModelingToolkit going forward. So to begin with, I'm going to talk about an example that if you've read our documentation, you've probably seen a lot. It's a simple DC motor. We have a voltage source that's connected through a resistance and inductance to a back EMF, which then spins a shaft and then has a load attached to it. In the simulation, the load starts out at 0, and then we have a step change, and then it causes the load to slow down. Apologies, I'm a little bit out of breath. In continuous time, it would be nice if it span at a consistent speed, and to achieve that, we can attach a simple PID loop to it. You can see here that it starts up, we have a little bit of underdamped behavior, it then stabilizes, we then have the step change in load, and then we see a burble and then it stabilizes again. With the new support that I'll be talking about today, we can then add a discrete time controller to it. So instead of the controller updating continuously in continuous time, we can instead have it updated at a certain rate. So here it's running at 100 hertz. And you can see that we're ultimately having the same response, albeit with a slight phase delay. But here the controller is now discretized. But ultimately seems good so far. But the thing is that getting an actual angular velocity measurement off of the load is kind of unrealistic. There are sensors that can do this, but they're expensive and annoying and don't want to add that. So what if we just had an encoder, right? Frequently you'll have like an encoder, it'll just give you a pulse every time it spins a certain amount. Should be good, right? Like we attach this thing, we differentiate it, seems reasonable. So we can do that, and everything goes to hell. So you can see here that once we add this more realistic encoder, so this is a quadrature encoder, and I'll talk more about what this means in a little bit, we are unable to effectively control the plant. It no longer reaches a steady state. And we're seeing all this noise, and it's just ew. So I'll talk about why this is happening, how we're modeling it in dyad, and sort of how we can use this going forward. So we've talked a bit about this before in the context of MTK sample data. But the idea is, behind both synchronous programming and these discrete events, is that instead of having continuous events that hold for all time, for every point in the real numbers effectively, we instead have these equations that hold only a discrete time. We can also, because we now have these distinct times, much more easily and much more commonly talk about times that are integer times, a certain number of integer times in the past. And that's all represented this way. In some of the new stuff, though, we also have a number of different clocks that we can use to discretize time like this. So there's the periodic clock, like I talked about earlier, which just runs at a fixed rate. But we can also have things like event clocks, where the clock is created by a continuous parameter that's crossing 0 that you can construct in any way. One second. And then there's a whole bunch of other clocks that we both have and are currently working on supporting, like a computed clock where you decide the time in the future that it'll run, or a one-shot clock where you get exactly one update and that's it. But these are the ones I'll be talking about here. We also have the ability to have hybrid systems. So here we have on certain discrete intervals, we say, oh, we see that you've achieved 1. What if you achieved -1? And here that causes the system to sort of oscillate back and forth as the continuous time system tries to track the discrete time output. We can also refer to history. So here I'm implementing a very simple discrete time finite differencer. So this is sort of your first derivative approximator in discrete time. And here I'm able to say that the slope between these 2 points is the difference between the current value and the previous value divided by the amount of time it took for us to get from here to there. So yeah, So in the model that I showed you earlier, we have 4 clocks actually. There's two signals that are coming off of the encoder. So there's 2 sensors on the encoder that are giving us sort of chopper signals. I'll show you this in a second. They're then being mixed together and decoded to tell us how far the wheel has actually spun. And then on this sort of synthetic clock that's built out of these 2 initial clocks, we're then adding up those steps that we've taken so far, differentiating the added output, and then we're sampling the value in that in the summer and differentiating it on a constant clock, which is then where we do the closed loop control. So this is also both supported in ModelingToolkit and Dyad. So at a very high level, I won't go into too much detail here. This is the discrete time Dyad model. It just wires up what you saw in the previous slide. The encoder, this is ModelingToolkit. This shows, again, a little bit more of the zero crossing clock semantics. What we do is we just create a zero crossing, which is effectively just a ModelingToolkit callback, and then that's used to sort of set off equations that occur on that zero crossing. So here, the continuous time events that we're actually observing are created by 2 different sine waves. One of the sine waves is pi over 2 offset from the other sine waves, so we get 2 out of phase. So we have 2 sine waves that are out of phase, and then we're watching the zero crossings. So to illustrate what this looks like, here's a sample of the data from the run. So the yellow curve is, I think, the A channel. The blue curve is the B channel. So the yellow channel here is created by the zero crossings of one sine wave. The blue channel is created by the zero crossings of the other. And then this creates the quadrature signal representing like a physical chopper wheel going past a couple of sensors. Just to show you a little bit more of the synchronous diode semantics, here is how we would write an accumulator, which just takes the current value and then which takes the last value and adds the current value to it, and a finite difference, which works the same way as the ModelingToolkit one that I showed you earlier. The decoder is a little bit more interesting because we don't have a single clock that the decoder needs to run on. Instead, the decoder needs to run on the union of 2 clocks. It needs to run on both encoder signal, on both sensor signals that we're getting to create the decoded encoder output. So what we do is we take the signals that are coming from each of the sensors, we then merge them together, so this creates sort of the OR clock of both of the inputs, and then we resample them using the last value mechanism here onto the union of the 2 clocks, which we then send into a state machine-like decoder that then figures out whether the wheel has stepped forward 1 step, stepped back 1 step, or hasn't moved on this particular clock. So again, as sort of an example of this, what we then end up with is that it takes in this sequence of events where we get the chopper signal coming in, and then it turns this into a 1, a 0, or a -1 that happens on the clock of the 2 encoder inputs. So here, the value is all 1, which is why I've plotted it using points instead of lines. The line plot version of this wouldn't be very interesting. But here, the simple presence or absence of a point is what's interesting. The times that they're happening at is really what's encoding the information effectively about how fast the wheel is spinning. Then stepping through the model a little bit more, we have the accumulator. So now we're adding up these events over time, and you can see that as the wheel spins fast, as we get these points closer together, the wheel spins faster, and as they get farther apart, the wheel spins slower. And as a consequence of this, the summed result, the encoder steps that we've added up, is a slightly lagging discrete time approximation of the real rotation of the wheel, as you'd expect from an encoder. It's doing what it says it does. But where we start seeing the problems is when we go and finite difference it using the block that I showed earlier. In yellow is the real angular velocity of the wheel, and then the blue is the discrete time velocity estimate that we're forming by finite differencing the inputs. And you can see here where all that noise that the PID controller was producing is coming from. Because what the PID controller is being told is, wait, you're going this fast now. No, we're going this fast. No, you're going this fast. Even when the actual speed of the wheel isn't changing that much. So why is this so noisy? It becomes much more obvious when I take this out of an angular space measurement and put it instead into the raw counts that the differentiator is dealing with. So In the angular space, we're looking at values of like 0.9, but this is actually coming out of us having turned 6 steps, essentially, or 7 steps, or 5 steps. And the difference between 5 and 6 and 7 is pretty substantial in relative terms, and that's what's creating this. Since the encoder wheel can't resolve steps in between them, we're sort of getting like 5, 5, 5, 6, 5, 5, 5, 6, because the true value is actually sort of, there's this sort of residual that's adding up over time. And that's being shown off by this multi-clock discrete-time model. So as a consequence of looking at this model, there's a number of ways that we could use to fix this problem. One very common solution that you see in real motor control, for example, is to use a more sophisticated filter to estimate the velocity of the wheel. So you could use a phase-locked loop, for example. We could target a faster set point. 1 radian per second is not actually all that fast. Or similarly, if this is a gear motor, we could attach the encoder to a different part of the mechanism that's spinning at a higher speed. We could use an encoder of a higher CPR. This was a 4,000 CPR encoder. You could use a 32,000 CPR encoder. Or you could, as I mentioned earlier, you could use a resolver that returns a true velocity signal from this. So in terms of how we implemented this, what we do is we take like a dyad or a modeling or a compiled modeling toolkit model, and then we split this up. We split this up into a continuous time part and a discrete time part by running clock inference on that resulting system. The continuous time part goes off and does its normal thing. We don't modify that path. In the discrete time part, what we do is we take the equations that are on the discrete time partitions, we then convert them into heptagon code. I'll explain what this is in a little bit. And then we pass this off to the hep-C compiler. The hep-C compiler takes that heptagon code, mangles it into C output, and compiles it into C. We then compile that C code into an executable binary, which then gets linked into the rest of the modeling toolkit model and is used to simulate the system going forward. So to talk about heptagon a little bit, heptagon is a compiler for synchronous programming languages originally developed at INRIA. What it does is that it takes these equations on clocks that we're producing and turns it into imperative code by causalizing it. It does a bunch of other checks, but we statically guarantee that you won't actually run into these, at least if I did my job right. Importantly, we actually also support FFI down into this lower level, and this allows you to do sort of low-level mangling of clock signals and data that's running on them. In the longer run, we aim to replace this with a more pure Julia solution, but this gets us going. This is a nice way for us to deal with these multi-clock systems. So as a quick little example of what this compilation process looks like, we take a modeling toolkit or dyad model. Here it's a very simple delay element. We then compile it down into heptagon or a Lustre-like code, and then that gets compiled into C code. This is obviously a very small snippet. So in conclusion, we now support hybrid multi-clock systems through modeling toolkit and Sync toolkit. It's ultimately based on synchronous programming semantics, although I didn't talk about that in too much detail, and with the goal of replacing Julia Sim compiler as the discrete time backend for modeling toolkit. It's currently based on heptagon, like I mentioned, but we're looking at synchronous extensions to Julia in the longer future. We want to have a number of additional semantic features like state machines, structs, and arrays, and fully integrating them into the rest of the discrete time semantics. And ultimately, we hope to release Sync Toolkit in the near future. I say a few months here, but it's probably going to be faster than that. OK, thank you very much.
All right, we probably have time for a question until the next speaker sets up.
Anyone? OK.
If not, let's thank Ben once more.
Oh, you had a question?
Please.
Did the semantics that we're using here support what would happen if 2 events happen at the same time?
Yes, they do.
Okay.
So we actually do see that a little bit with the encoder output, and that what'll happen here is that we will like compute the union of them, and you'll only get one event out if both of these were to happen at the same time.
All right, let's thank Ben once more.